So we left off here, and we were talking about these grignards, or these lithium compounds, and the warnings that I told you to keep out with a look for, because any type of water or acidic proton will cause you a problem. But once we get these, what can we react with them in order to get some type of product? What would be the purpose of these? Well, there's a couple of different things that we can do with them. And really, what I'm going to say here is anything is fair game. Why do you mean anything? Let's go back to basics on a garden time. These carbons, folks, are negative, which means that these are nucleophiles. And these nucleophiles can react like any other nucleophiles that are out there on the market. That's all that we've talked about. Alkene reactions, alkyne reactions, substitution reactions, elimination reactions. They all involved a nucleophile and electrophile. Therefore, anything's fair game. So let me give you an example. Let's say that we had CH3Li, and we just talked about an epoxide. There we go. These two things will react. Huh? How do I know? You should know that too. This is why. You are now acquainted with an organometallic, and you know what this is going to do, right? This lithium is squiggly positive, and that carbon is squiggly negative. There's some polarity difference due to electronegativity. All right, well, this is negative, and I need to point it to a positive piece. All right, so here's an epoxide that we just learned about in the last lecture module, so that's why I'm using it. Do you think that carbon's going to be pointed to that oxygen? Why not? Well, look, it's got some electrons here. There's electron pairs. This is negative. Why would that go to a negative place? It doesn't want to go to a negative place, just like you don't want to go to a negative place. But when you're taking organic, you might be in a negative place, and I'm sorry if I depress you. It wasn't my decision. So I need to take this to a positive piece. If I look at this molecule, the oxygen's negative, the oxygen's electronegative, the oxygen's going to be the electron sucker. Where does it pull the electrons from? It pulls them from the carbons. I mean, it's the same old rehash of story over and over and over and over and over. There's nothing new here. So these carbons are going to be partially positive, which means that this partial negative carbon will come in to one of those carbons and it will attack it. And that carbon says, oh no, I'm being attacked. Oxygen, you gotta go. So pop, off it goes. It can't have more than 4 bonds. There's nothing new here. The only thing that we're doing is throwing a metal in so that way I can get carbon to attack. That's what's new. The rest of the mechanisms are all the same. Okay, so I'm going to draw the epoxide. That's what I normally like to do, right? I start off with my starting piece, and that looks like this. And now what we're going to end up doing is we are going to pop, off that goes, and that's because there's a new bond in town, and that new bond is going to be with that methyl group. Okay, well, what happens to this oxygen? Well, right now it's just negative. There's nothing there for it to take. Now, this lithium could come around, right? That lithium is positive. So this lithium could hang out for that oxygen for a while and just like talk crap about what happened to the last weekend. It's just like chitter chatter. But in round number 2, after we allow this reaction to happen, we could end up adding some kind of acid to it. At this moment, acid's going to be okay because we've already allowed the first part of this mechanism to take place. We don't have to worry about destroying the grignard. So we can add acid into round 2. And what happens is that that lithium will kind of be overtaken by the acid, and this will turn into an OH like the epoxides have always turned into. And look at what we've done. We have started with an epoxide that has 2 carbons, and we've made a product that has 3 carbons. There's your magic. Organometallics do an extremely well. What they do extremely well is chain elongation. Folks, we've not really talked about chain elongation that much, right? We saw it in the triple bond reactions back in Orgo 1. Back in Orgo 1, we said, you can take acetylene, and here is acetylene, and we react this with NH2, an amide. And what happens is that the amide will go in and rip that hydrogen off. And what we end up with is a carbon, triple bond carbon that carries a negative, and then this becomes a nucleophile, and that nucleophile can then react with other things, and we can chain elongate. Do you remember what we did? Well, we added on things like 1, 2, 3, and then a bromine here. So we talked about the acetylide coming in and attacking that carbon and that bromine leaving. And all of a sudden we would end up with a carbon, 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 and then the new piece, which is a carbon, triple bond, carbon H. This was a chain elongation step. This was also a substitution reaction. Bromine, the alkyl halide, was substituted with the acetylide. Folks, it's all coming back to me now. Celine Dion told me it was going to be, and here we go. That was an alkyne reaction presented in Orgo 1, mixed in with a little bit of substitution at the end of Orgo 1, and now we're seeing that this is actually getting applied some form or fashion to organometallics. Yes, and here's why. Look at what you did. In this setup, your amide pulled a hydrogen off to create a negative piece. What are we doing with organometallics? We're making negative carbons. So even though we are targeting organometallics, we have already been using negative carbons. This is not a new concept to us. This goes all the way back to the middle of Orgo 1. So this negative carbon is a carboanion, and that carboanion attacked the partial positive carbon in that reagent, kicked the bromine off in this case, and pew, away it went, and it substituted. And we elongated a chain. The same thing is happening here. It's just starting with a metal, because this is another way that we can get those negative carbons. We don't need acetylide. We don't need the C triple bond C in order for this to happen. There's another option out there for us, and this is that option. So CH3, CH2, and then maybe MgBr that comes along with it. There's a Grignard. So let's react this with an epoxide. So here's carbon, carbon, and there's my O. And then let's put a carbon here and a carbon there. I mean, that wasn't uncommon either. It's just a bigger epoxide, right? No big deal. Let's make it a little trickier. Let's not make it symmetrical. Let's get rid of that one. Let's do this. Now, can we put the pieces together? I hope so. We just talked about it. So this carbon is going to be slightly negative. That means that's the nucleophile, folks, and it's going to go to a positive piece. In the epoxide that we have right here, where's my positive? It is not at the oxygen. I'm sorry, it is not at the oxygen. You should know better than that. It's going to go to one of these carbons down here. That oxygen's electron greedy. It's seeing two things at one time. This is a three-way relationship. That oxygen's pulling both from both directions. This is a base. The base is going to come in. Ding, ding. And it sees these two carbons, and they're both miserable in that relationship. And that other negative carbon is going to say, hey, you're not happy. Why don't you come on over? We'll watch Netflix and chill. It's just got to figure out which carbon's going to fall for it first. I mean, that's the thing. It's the path of least resistance. So this is a base. Do you remember what epoxides did with bases? Well, this epoxide would look at these two carbons and say, the base is getting ready to take one of you. One of you all are cray-cray. I don't really want to deal with the cray-cray one. So this carbon, hey buddy, come on over. Can you pick out which one the cray-cray one is? It's the one that's the least stable. Out of these two carbons, which one's the least stable? And I hope you're going to tell me the one to the right, because this is primary and this one's secondary. So if that carbon comes in and plink, there it goes. That oxygen says, whew, gosh, okay, the cray-cray one's off, the cray-cray one's distracted, and now I can go on to this secondary carbon, which is a little bit more stable, and I think this is going to give me a better relationship. So if that's what happens here, that's great. What I'll have is I'll have this piece here. I'll start off right there. This CH2 has now been added on to this carbon, CH2CH3. This bond has now been broken. There it goes. And a hydrogen will eventually add on to that oxygen, because in step number 2, they will write some type of acid. They can't just leave that O- hanging out there with nothing attached to it. So they typically will end these with hydrogen every single time. Either H plus or HCl if they want to be specific on the acid. Well, let's clean this up a little bit. We're going to clean it up. Carbon, 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 and then another carbon and another carbon. And then off of this second carbon, I'll have an OH group. All right, so I'm going to take that back on, and let's talk dirty. What? What do you mean talk dirty? That could have made some of you all excited. Let's talk organic. Here we have ethyl magnesium bromide. And that ethyl magnesium bromide is going to react with this epoxide. This epoxide and ethyl magnesium bromide, which is a Grignard reagent, will produce an alcohol. And this alcohol is 1, 2, 3, 4, 5. So pentane, but drop the E at OL, and that alcohol is at the number 2 position. This reaction is happening just like a nucleophilic reaction would. So ethyl magnesium bromide reacts as a nucleophile to attack the primary carbon of this epoxide ring. That allows the oxygen to break this bond and free up the primary carbon, forming a more stable secondary alcohol, and that secondary alcohol will be 2-pentanol. With the addition of the Grignard reagent, we have also elongated the chain. So we have started with a 3-component piece, and now we have ended up with a 5-component piece because the 2 extra carbons have came from the Grignard reagent. Folks, that's where we're headed. Again, it's all about the basics. Never lose sight of the basics, and I think that if you never lose the basics, you could answer possibly all the questions in organic that they ever want you to answer. It's just figuring out charges. What's it doing? Once you learn the mechanism of something, folks, it really is applied to everything. But it's just a matter of what's my positives, what's my negatives, and that will allow me to critically think about these types of reactions going forward. Okay, so let's now look at a few more examples. This reaction, or this example, says react the 3 down below with ethylene oxide, and then expose it to acid on the second step. They put that in parentheses just to kind of go, hey, don't remember that O can't be negative. You got to put something on it. Okay, no big deal. So ethylene oxide, F is 2, so here, 1, 2, and there we go. So I'm going to shorthand this. I hope you know all the hydrogens are where they need to be. I think we can skip that point at this time. Propyl magnesium bromide. All right, so prop, 1, 2, 3, magnesium bromide, MgBr. There we go. This carbon is negative. That carbon will come in and attack to one of those carbons. That breaks the bond, and up it goes. So there is my mechanism. Look at how easy that was, right? So here I have my epoxide, and it didn't really matter which one I attacked. And the reason it's a symmetrical epoxide, whether you attack the left or right, who cares? I don't care. So get rid of one of those bonds, and that side of attachment will add on another 1, 2, 3 carbons. So 1, 2, 3 carbons, and there you go. That oxygen cannot stay negative, which is the purpose of adding the acid. So we erase that negative and we add an H, and we get a alcohol as a product. What is that alcohol? 1, 2, 3, 4, 5 carbon chains. This is a 1-pentanol because my OH group is attached to carbon number 1. Was that hard? Were you able to follow through with that? If so, you're doing your job. If so, you're learning organometallic reactions. So if you felt okay with that, good for you. I'm doing my job and you're doing yours. Now, let's take a look at number 2. Number 2 says benzyl magnesium bromide. Okay, whatever. That's not going to scare me up. There's my benzene ring, and then here is my MgBr. So there's benzyl magnesium bromide. And look at this. I'm slipping. Let me go back. Where's my eraser? Benzyl magnesium bromide. That was phenyl magnesium bromide. So benzyl is an extra carbon. You don't know that yet. We haven't really talked about it, but I almost fell for it. And we're going to react this with ethylene oxide. So there we go. What's going to happen? Nothing. Nothing different than what we've already talked about. This is a negative carbon. That negative carbon is going to be attracted to that positive carbon. It doesn't matter which one. They connect together. The oxygen pop opens up and we put an OH on it. So what kind of product gets formed? Here is my carbon and my carbon of the epoxide. And then off of this, I have a carbon that got attached. And that carbon's bringing with it to the party a bunch of friends. And those friends are going to be a benzene ring. And then over here to the left, we have an O. And that O is going to get protonated from the acid, so that turns into another alcohol, and there we go. That's number 2. Okay, well, what about the last one, number 3? It's no more difficult than the other 2. It's just reconfirming what we've learned. It's cyclohexyl. All right, so cyclohexyl. There's my cyclohexane ring, and off of this thing is a magnesium bromide, and I'm going to react this with the ethylene oxide. So there we go. Well, that magnesium makes this carbon negative. That carbon is going to be attached there, and this is going to open up. Pop, open goes the ring. And we need to add on a hydrogen to that oxygen. So what do we end up with as a product? Well, here are the 2 carbons in the epoxide ring. And this carbon of the ring is right here. So that ring is brought to the party. So there we go. There's my 6-membered ring, but that's pretty sloppy, but you get what I'm saying. And then off of this carbon, we have an oxygen. That oxygen is going to eventually get a H from the hydrogen. So there you go, folks. There is your intro to Grignard reagents. There's your intro to lithium compounds. Lithium would have worked the same way that magnesium bromide was working in these reactions. There's no difference here. And I do want to confirm to you that alkyl halides, vinyl halides, and aryl halides are all okay with these. Perfectly fine. These have caused us some problems in the past. They'll cause us problems in the future. These are the ones, especially the vinyls and the aryls, because their electron core is so dense and so negative, and delocalization and stuff on them sometimes as well. It's just really hard to react with them. But not in the world of organometallics when lithium and magnesium is concerned. The only drawback down here at the very bottom, everything has to be completely dry. So once you form these, that is a nucleophile, that is a negative source, and you treat those negative sources like you have treated them in any other reaction up until this point. There is no difference. All right, so what's up next is this idea of transmetallation. What is transmetallation? What does it do? Why is it important? How can we predict it if it happens? And that's what we'll focus on in the next video. So we're moving on. There's our Grignard. There's our lithium. But folks, there are more organometallics that we need to focus on. And before we get to that point, transmetallation has to be discussed. And you'll see why next.